Hi, everybody. This week, we're going to start our discussions on repeated measures models and longitudinal designs. And before we get started, I know we've spent a lot of time this semester working through the regression module in SPSS. So I'd like us to kind of take a minute or two, maybe 20, to talk through the similarities between the regression procedures that we're familiar with and the GLM procedure in SPSS. And this will help us really move towards using the GLM procedure for repeated measures designs. So I'm going to go ahead and share my screen. And the example that I want to work through first is not repeated measures, but it's one we're really familiar with, and that's the physics data. So we're just going to look at how we can answer really the similar questions in regression using the GLM module. So I'm going to go ahead and share my screen. So our physics data, like I said, we have a whole collection of variables here. Two of them that I want to make sure you're, excuse me, familiar with is the categorical variable. We have one categorical variable called sex, which is coded as 1 for males and 2 for females. And I recoded that as a dummy coded variable, which we've done repeatedly in regression, with a 1 for males and a 0 for females. So you can click on variable view and see how those are coded. So 1 is male and 2 is female for sex, and 1 is male and 0 is female for the sex 0, 1 variable. So I've put the syntax and everything on Carmen as usual, and I have annotated printout that I'm going to walk through so we can see what's going on. And when we get to the GLM piece, I want to actually show you the screens as to how that's done. So we're going to start by looking at the annotated printout. Actually, I'm always concerned that it's not sharing the screen I want. So I'm going to just stop for a minute and make sure that I am absolutely sharing what I want. Okay, so this is our PDF of the regression to GLM modules. As I said, we're using the familiar regression data that we've used in a lot of our examples, the physics data that we've used in a lot of our examples this semester. So the first thing, that we do when we're getting familiar with data is to just run some, frequency distributions on the variables of interest. So in this example, the dependent variable is the physics score. And I'm using just the variable sex to begin with here, so we can get familiar with the data. The mean on physics was a 79.57. And you can look at all that data. You have it in front of you. One thing I wanted to point out is that there are some missing observations. For physics, there's only 195 complete observations. So we just want to keep that in mind when we're looking at the results and interpreting the values that we see. The first histogram is for math SAT, slightly skewed. Then we have verbal SAT, not really particularly normal. Gender is balanced. Creativity looks relatively normal, and so does abstract thinking. And physics, of course, is our dependent variable. Remember that the assumption in regression, true even if we're using regression through the GLM procedure, is that the residuals themselves are normally distributed. So not so much what the dependent variable or the predictors look like, but what do the residuals look like when we run a regression model. So the first example is using regression, and I'm using the sex 0, 1 variable. So it's dummy coded, so I can include it in that form in regression. And these examples are uncentered. We're not going to really worry too much about the intercept so much. Just in this review, we're really looking at what's happening with the slopes and how things can correlate between the regression commands and the GLM commands. Now, overall, we have 194 complete cases. So all of these procedures will really run only on the complete data that's available. From our model summary, so here's our predictors. We had 5 predictors. From our model summary, we get an R-squared of 79.6, which is really quite good. That means 79.6% of the variance in physics scores can be explained by the 5 predictors as a set. And as you know, the R-squared we can also find from the ANOVA table, which is just the sums of squares for the regression divided by sums of squares total. And this regression, this ANOVA table tells us that the model is statistically significant for the 5 predictors. So at least one of the predictors has a slope that's different from 0. In our coefficients table, we can actually now look at what our y-hat model will look like. So again, if I was going to write out this y-hat model, this is uncentered, so we're not really too worried about what the intercept looks like, but our predictions would look like 0.379 times the math score plus a negative 0.09 times the verbal SAT plus 7.246 times the dummy coded sex variable. So we want to remember that 0 was equal to females here and 1 was equal to males. So we'll interpret that in a second. Plus we have our remaining variables, 0.302 times the creativity plus a negative 0.282 times abstract thinking. So just looking at these slopes, we can see that the math, verbal SAT, and sex are statistically significant. So they are the variables that help to predict differences in the dependent variable of physics. Creativity and abstract thinking were not significant in this model. And we also see that abstract thinking has a negative effect, even though it's not statistically significant. Verbal SAT also has a negative effect. So as verbal SAT increases by 1 unit, physics scores are predicted to go down by 0.09 points. Math SAT, however, has a positive coefficient. So as math SAT scores increase by 1 unit, the physics prediction goes down by 0.379 points. For sex, the sex variable, recall that that's dummy coded. So the difference between males and females is 7.246. This is adjusted for all the other covariates in the model. So it's like the adjusted difference between males and females. And it is statistically significant. So that difference, 7.246, is really telling us about the difference between males and females in terms of the physics outcome. Now, some other things we want to just remind ourselves of for the regression analysis is the tolerance. They all look really quite good. And also the column that says partial. Remember that partial refers to the variance. When we square it, it's referring to remaining variance in the dependent variable that's explained by that particular variable. For example, if I take this math partial R squared, so I want to take 0.837 and square it. I get a value 0.700569. So 70% of the remaining variance in physics achievement is explained by math SAT after controlling for all the other predictors in the model. And that's how we can use that partial correlation, or the partial correlation squared, to help us understand really what we mean by the effect of a predictor in the model. We can also use the part squared to help us understand the effect of any predictor. The word we associate with part squared is unique variance, whereas the word that we associate with the partial R squared is remaining variance after the other variables have been included in the model. Just scanning down the part correlation column, we see that math has the highest part correlation. Doesn't have to be positive to be considered the highest, so it's highest absolute value. So the greatest proportion of unique variance explained among these 5 predictors is through math SAT. And if I square that, 0.690 squared, I get a value of 0.4761, which is really quite sizable. 47.61% of the total variance in total variance in physics can be explained simply by math, given the other variables that are in the model. The overall R squared was 79.6, so that's about half of what we explained with the model to begin with. So next we have our collinearity diagnostics table. And, you know, it's kind of interesting to look at this now. For collinearity diagnostics, the largest condition index is definitely greater than 30. But when we look at each variable separately, each of the 5 predictors separately, they're all loading on only one of the dimensions independently. So that's not really anything that would give us cause for concern. Recall that our diagnostic here is that if the condition index is greater than 30 and 2 or more of the variables load on the same dimension, that could indicate a problem with multicollinearity. We don't have that situation here. And in addition, all of our tolerance values look very good. So from that, you know, just to summarize what we've seen there, looking back at the coefficients table, we have 3 variables that are significant in this model and 2 that are not. And it seems that math seems to explain the largest proportion of variance in the dependent variable. So now we're going to use the GLM procedure. And the first thing I'm going to do is to use sex 01, which I dummy coded as a covariate. Now, whenever you're dummy coding something for an analysis, you can actually include it as a covariate because you've already taken care of the fact that it's a categorical variable. So you do have options as to how to include a categorical variable in the GLM procedure. But in this first example, I'm just going to include it as a covariate so we can match up the results from the GLM model to the regression results. Now, I do want to take a minute to kind of walk you through how we would set up that GLM model using the menus. And then, of course, you can edit the syntax as you see fit. So the first thing we see is our data. You know, you can look at data view or variable view. So we're going to go to Analyze and choose General Linear Model and choose Univariate. We've done this several times before, so I'm hoping this is really a reminder or a review. So our dependent variable is physics score. So I'm going to bring that up to the right-hand side where it says dependent variable. I think my screens might look a little different from yours now because I added an extension and it changed how my SPSS looked. So don't be alarmed that my screen might look a little different than what yours do. Now, as I said, we were going to use sex01 as a covariate because I've already dummy coded it. So I want to bring in all the variables that we had in our previous example, but I'm only indicating that they're covariates. So I'm bringing over math, verbal, we had creativity. Oh, actually, I added sex next. So I'm just going to try to keep them in the same order. They were in regression, so we'll be able to make comparisons more easily. And then we had creativity and abstract thinking. So those are my 5 predictors. Okay. And now I'm going to go through each of these screens. In our model, it's just, we don't have any factors that we've identified here, and there's no interactions. So I'm just including these as a full factorial model. Notice that it's using type 3 sums of squares. That's the default. And we've talked about that before. That just corresponds to our discussions on remaining variance after other variables have been included in the model. So it's still in that same frame as how we think about regression. And of course, I want to include the intercept in my model. So I'm not going to change anything on that screen. Contrast, I'm not going to change anything here because I don't have, again, I haven't defined any factors, so I'm not going to worry about that. For plots, I don't have any factors, so I'm kind of limited as to the kind of plots I can create with the GLM, but that's fine. I'll show you in the next video after this how we can make a lot of plots in addition to what might be the ones we're constrained to in the GLM package. EM means we don't have any factors that we're comparing, so I'll skip that. We're not going to save anything. And for options, I want to include descriptions, descriptive statistics. I want estimates of effect size, and I want the parameter estimates so that we can see what's happening with how it relates back to the regression. None of these others are going to make sense for us in this example. We don't have any homogeneity tests because I haven't identified any variable as a factor. So I'm just going to choose those 3 and I'm going to click continue. And then I recommend using paste. You can look at our syntax in the SPSS window. It's always way down the bottom. So I'm going to go ahead and run this. And then this corresponds to the printout that you're looking at in your annotated printout. So I'm going to go back to the PDF. And now we're looking at, this is where we ended. So we're looking at the GLM procedure. So you can see that the language here is exactly the same as what we pasted on the previous screen. And the one thing I want to point out is this with command. So any of the variables that follow the with command are being treated as covariates. That means you've either dummy coded them in the way that you want them dummy coded, or they're continuous. So all of our variables, including sex01, I'm including after that with statement. The next statement is sums of squares type 3. That's the default. And again, that corresponds with our understanding of how variables contribute to remaining variance after the other variables have been included in the model. We wanted to make sure we asked for effect sizes, descriptive statistics, and parameter estimates. And in our design statement, you can see we're listing all of the variables that we included in our model. Now, the first thing we see is that we get a mean for our physics variable. It's the same as what we saw before, 194 complete cases in our analysis. So now we get our ANOVA table. This is actually what we might refer to as an expanded ANOVA table. Now, the 3 that I have highlighted in yellow, the sums of squares for the regression, the sums of squares for the error or the residual terms, and the sums of squares for total show up in a very different way in the GLM procedure than they do in the regression. In regression, we're only seeing these three elements. And the SSR is really, this is the same F, and the model is statistically significant. So it's the SSR, also referred to as the corrected model. That's just language that GLM uses, is really telling us that the model with the 5 predictors is statistically significant. You can see that the R squared, it's referred to here as partial eta squared. The R squared for the overall model is 79.6, exactly what we had in the regression. And we also see that kind of listed at the bottom of the table, R squared. We can also find by taking SSR, that 46,000 divided by SST, the 58,000, and that will give us the 79.6. Now, the GLM procedure also gives us some extra pieces of information in this ANOVA table. This column does not sum to the 58,095, as you can see by looking at it, but the pieces that will sum to the 58,095 are the regression sums of squares and the error sums of squares. Now, these sums of squares won't sum to the 46,253 because there's overlap in the variables, but that doesn't really interfere with our understanding of how to interpret the information in this table. So we have our 3 components of total of variance in physics, and each one of those, or well, the sums of squares for the regression, we already talked about that, is statistically significant. So what about the 5 predictors? So we had 5 predictors. Each one of those predictors in the model takes up 1 degree of freedom. So that's why they all have the same degrees of freedom here, and they all total to 5. And then we have our, these are F statistics. This is the test of whether or not each of those variables is significant in the regression model. It's a GLM procedure, but it's still regression. And we can see that MSAT, verbal SAT, and SEC01 are all significant. They're exactly the same p-values that we saw in regression. And as a matter of fact, these F statistics, if you recall from an earlier discussion a long time ago, if I take the t squared from the regression, I'll be able to compute the F. So let's look at what's happening with math SAT. So the F statistic there is 439.526. So I want to see how I can duplicate that. Sorry, 439.526. This is for math. I want to see how I can duplicate that from the regression t statistic. So that's a 20.965. So if I take that t statistic and square it, 20.965, I'll get that 439.526. So we can just do that out quickly just to verify. So 20.965 squared gives me 439.53. So with rounding, it's coming out exactly the same. So the F from the GLM will always, whenever there's 1 degree of freedom, will always equal the t squared from regression. So we can see we're getting the same information about the significance of the variables in our model. It's the same 3 variables as we saw in regression. The other piece we can see here is the partial eta squared for each of our predictors. We have 5 predictors. Now here, the GLM procedure is giving us that partial eta squared exactly. So it's taking the partial correlation that we know about from regression and squaring it. So it's providing an effect size. So for example, if I take the partial correlation for math from the regression, that was a 0.837. I'll just show you again where that comes from. Right here, 0.837. If I take that partial correlation and I square it, I'll get the partial eta squared. So that's the 0.700. And each one of these corresponds to that partial R from regression squared. So again, GLM is telling us the same information about contribution of variables in the model, just packaging it in a slightly different way. The other thing I'd like to point out in this ANOVA table is that we don't interpret the intercept sums of squares, and we don't interpret what's called the total sums of squares. So it's really important that you remember that it's the corrected total that we want to keep track of for those two entries. Let me see where I can write that down. So the total, what GLM is calling total, is just the sum of all the observations squared. And then the corrected total is our familiar sums of squares for the total. So that's the sum of y minus y bar quantity squared. So it's always that corrected total that we want to use, say, in the denominator for the R squared. It would be very rare that we would ever be interested in the total or what GLM is calling the intercept. It's we need to know a lot more about, say, matrix algebra in order to understand what's happening there for the intercept, but it's of no value to our interpretation of the ANOVA model. So I would just cross those off and not worry about them any farther. And in published papers, those entries for the intercept and the total are excluded. It would be extremely rare that they would be included in the ANOVA table. Now, the next table we see are the parameter estimates. These are all exactly the same as what we saw in our regression model. So our y-hat model, we can organize this in the same exact way. 62.945 plus ... We can write that all in the exact same way. And that's because we had SEC01 is already dummy coded. So it's actually going to be included in the model, 0.7246 times SEC01, as we saw in regression. And again, this is a difference in adjusted means because SEC was dichotomous here. So we can think of it as a difference in adjusted means, adjusted for the other predictors in the model. And we also see that SEC01 was a 0 for females and a 1 for males. So we could actually write two regression equations. We could write one for females and one for males. And the female regression equation just would not include that variable for SEC01. Now, this model, of course, we've talked a lot about analysis of covariance and interactions between categorical and continuous predictors. You can do all of that in the GLM as you can in regression. In this analysis, we're just trying to match up how they correspond, the regression output to the GLM output. So I didn't worry about testing for homogeneity of slopes or anything in this particular analysis. I just wanted to make sure we could correspond the regression to the GLM. So we see our same three variables are significant. Here's the same three T statistics. Again, if I square those, I'll get the F statistics in the above ANOVA table. We get our partial eta squared. Again, I'm not going to interpret. Oops, I didn't want to delete that. I don't want to interpret what this partial eta squared is for the intercept because it's not particularly helpful. But the other partial eta squares for the variables, the predictors in our model, these are the same as what we saw from regression. If I square these, I'm going to get the contribution of each predictor to the overall model, controlling for the effects of the other predictor. So it's that remaining contribution that's being identified here in the partial eta squared. Now our next example is going to use sex in a different way. So here we're going to use sex as a factor instead of as a covariate. And I'm going to let the GLM procedure let me define how I want to code those groups. Now, this is a simple example because it's just dichotomous, but over time we'll see some additional ways we can code those predictors, okay, when they're categorical. So my choice here is I used a simple contrast for the factor. The default is actually to use polynomial, but I'm going to change it to just use a simple contrast. And a simple contrast is really each variable against another variable in the model, a comparison group. When we do that, we want to make sure we click change. I'll show you how to do this in a second. And I also want to keep the last category as a reference, which will match up with what I have. So if you think of, our sex variable was a 1 and a 2. So the last variable is going to be the referent group. So it's like creating a dummy coded variable for us instead of my having to create it using the syntax. So I'm going to go to the back to SPSS, to our data, and we're going to go to our GLM window again. So general linear model, univariate, and I'm going to reset this so that I can set it up with sex as a factor instead of a covariate. So our dependent variable was physics, and now my fixed factor, that's going to be sex instead of the sex 0, 1 variable. And then I have the same set of covariates. So I have math SAT, verbal SAT, creativity, and abstract thinking. All of those are continuous. They're not factors. Strictly speaking, a factor is a categorical predictor. And now I'm going to look at my different options here. So the model statement, again, I don't have any interactions and I only have the one factor. So there's nothing I need to do in that model statement. For contrast, the default is that it's not going to do any contrast. Yeah, so I misspoke earlier. What we'll see in another screen when we do repeated measures that the default contrast is polynomial. In a univariate model that's not repeated measures, you need to define what contrast you want. So we want to have simple contrast. So I have a handout also on Carmen that talks through all of the different options for contrasts in SPSS. So we'll look at that, or please look at that this week, and we can talk about it next week. So I want simple contrasts. I want to keep the reference category as the last, and remember to click change, or else it won't register for the syntax. So after you change that and click change, you can click continue. Here now I can have some plots with say sex on the horizontal axis. I want to do that. Let's have separate lines for sex. And then I have, oh yeah, and I just want to use a line chart. So let's just keep that as my plot. EM means, I'm going to skip this statement for right now because it's, we only have a dichotomous, it's the sex is dichotomous, so we don't need to worry about looking at the specific differences in means. So I'm going to skip that for now. And for options, I'm going to pick the same 3 descriptive statistics, estimates of effect size, and parameter estimates. And now that I have a factor in my model, I'm going to click on homogeneity tests. So this will actually do a test for homogeneity of variance between boys and girls on the physics outcome after controlling for all the other predictors in the model. So I'm going to click those 4 and click continue and then paste this. If I look at my syntax down the bottom, so this syntax is what I want to run. You can see that all 5 variables are still identified in the design statement. And now I have a by phrase. So I'm analyzing physics by sex because sex is a factor. So anything following the by statement is classified as a categorical predictor in your model. And then anything after the with statement are considered as covariates. So I'm going to go ahead and run this. And then once again, this is on your annotated PDF. This is where we are. So this statement here should align with exactly what we had going through the windows. So we have our contrast is using a simple contrast. That means it's just comparing one group to the reference group. And we defined the reference group as females. That was the last category, the one coded with the value 2. So when I say this, note the difference in syntax, I'm referring to the difference from the GLM model that we ran above. Now, because the factors are strictly categorical, the GLM routine will allow us to make comparisons across different levels. This is really similar to what we did when we had ANCOVA, when we were comparing adjusted means. So the GLM is a lot more flexible in that it will define some of these comparisons for us instead of us having to create the dummy codes and physically include interactions or comparisons in our model. Now in our descriptive statistics, well, first we can see that we have a slightly unbalanced design, but for descriptive statistics for the dependent variable, we can look at the mean for males and the mean for females and note that their raw difference is 12.5 points. That'll help us make sense of some of the output a little later in this same analysis. The next test we see, or the next result we see, is the Levene's test. And again, this is testing whether or not the variance for males is equal to the variance for females. The alternative here is that, of course, that they're not equal. And the p-value here is very large, which for a homogeneity of variance test is great. That means we're retaining our null hypothesis. And this this Levene's test is actually done on the data after adjusting for the remaining 4 variables in the model. So it's not just a raw HOV test on males versus females. It's actually controlling for the other predictors in the model, which is really nice. Now this ANOVA table, again, you can, think about this as the expanded ANOVA table. This ANOVA table is the same as our previous GLM, mostly because sex was dichotomous here. So everything is really going to be exactly the same. The sums of squares are the same. Of course, we're not interested in the intercept row or the total row. Corrected total is the SST that we want in our, say, our ANOVA table that we might publish in a journal article. We can see our overall R squared for the model is 0.796. And then we get our 5 effect sizes for each of the predictors. Those are the partial R squareds, partial correlation squared for each of the variables. So again, math is seems to have the largest proportion of variance explained, of variance in physics that's explained after controlling for the remaining variables in the model. Now we have our parameter estimates or our regression table. And we can see here that it looks slightly different because for sex, we actually allowed SPSS, the GLM routine, to categorize or code those variables in a way internal to the design. So that's 7.246. Again, this is just going to be the difference in adjusted means between the two values for sex. Here in this model, if we look at the significance column, math and SAT, of course, are still significant. It's the exact same model. It's just kind of packaged a little bit differently. And here we can see that the analysis is actually providing those two models. So we're getting one model for males. That's when sex is equal to 1. So we would add those 7.246 points to our prediction for physics achievement. The second model would be for females. Everything else would be the same, but we're not adding anything for the contribution of females, the way that we set up this model. So that coefficient for sex equals 2, that's females, actually drops out of the regression equation. So everything else is the same as the previous GLM and the regression. And because the variable sex is significant, the difference between males and females is also significant. That's the comparison being tested because it's dichotomous here, and the two levels being compared are just males versus females. Now on the last page, we get what are called custom hypothesis tests. These will only appear when we have a factor included in our model. That means that we've identified a variable as categorical, strictly categorical, using that by statement. And this is corresponding to what we requested, which were simple contrasts. So with simple contrast, one level is compared against another level. So you can see that the contrast estimate is 7.246. That was the differences in adjusted means that we saw earlier, and that difference is statistically significant. I'm going to pause this just for 1 minute. Okay, I'm back. I'm sorry about that, but wait 1 second. I'm sorry. Just my throat gets so dry sometimes, and I'm almost to the end, so I'm not going to restart the video. Where was I? Oh, we were talking about the difference in the levels between males and females. You can see that number 7.246 again. Like, this is just testing the difference in those adjusted means. Remember that the raw mean was about 12 point something that we saw at the beginning of this section of the printout. We also get confidence interval limits for our difference between males and females. The language used here, like level 1 versus level 2, not very convenient, but you just have to kind of have to keep track of what's actually being referred to. And it does tell you what the reference category is. So it's easy to figure out once you kind of get used to the presentation style. The very last thing is is the same information as this table, the contrast results, but in a univariate format. I would recommend just really focusing on what's in this table, the information that's provided there. There's nothing additional in the univariate table underneath. We get the same partial R squared as we saw for the gender effect above. So it's really not that interesting in this case. So now overall, what have we learned in this brief video? First, everything that we know about regression, we can do through the GLM procedure. That includes testing homogeneity of regression lines, using interactions, creating a polynomial model. We can do all of that in the GLM procedure. Everything is completely aligned with what we find in regression. Regression also gives us additional information. So if you only are doing regression, it's often easier to use that regression procedure. But in some situations, you might want the greater flexibility of using the GLM procedure, and that's especially true when we have repeated measures data. So everything we've learned about regression, we can do through the GLM procedure. They're exactly the same. Now, in these examples, sex was treated as what we call a between subjects factor, and that is a word that's used a lot in a GLM framework. We don't really refer to our variables like that in a regression framework because all of the variables in regression are considered to be between subjects. And in fact, all of the variables that we have for this example that I've showed you are between subjects anyway, because all of those variables only vary between people, but they don't vary within people. That means that the only changes in the independent variables are changes because the people are different, not because we have longitudinal data, in which case variables might change within a person. So this GLM procedure is actually a lot more powerful in terms of the kinds of data we can analyze than regression is, especially for repeated measures data. And when we have repeated measures data, we actually make a distinction between which variables change between people, like sex or verbal SAT scores. Those are different between people, but they don't change within people. Within subjects factors are a name we give to variables that actually change within people, typically over time. So that's our next topic, is to talk about repeated measures data. So now you have this kind of template that you can refer back to that will really help you think through how regression and the GLM procedure are doing the exact same thing. Okay. That's the end of this video. Thank you.